Thank you, Leah, and thanks to everybody out there today for joining us and your continued interest in the Commercial Crew Program and our Starliner crewed flight test. I hope everybody had a wonderful Father's Day. We did give our team the weekend off. They have been working long and hard all the way back to before the first attempts back in early May, so we decided to give the team a little bit of a break on the weekend. I'm going to try to give a comprehensive update of what has been transpiring since we last talked on June 6th after docking. The teams have been very busy reviewing the data and executing the on-orbit flight test objectives for the mission. I would say overall Starliner is doing very well on orbit. This is a test flight. We're taking our time to understand the vehicle and also understand the service module. The service module is a component that we don't get back. As you know, after we execute the deorbit burn, it burns up in the atmosphere, and so we're taking our time to understand that service module and the things that we've had happen relative to the helium leaks and also the thruster fail-offs at docking. Safety is in the foremost part of our mind as we approach the problems and look toward the return of Butch and Sunny. It's a test flight. Butch and Sunny are doing well. My clambers will talk a little bit more about that, but they are anxious to understand every aspect of Starliner that we can, and even as we got out on the weekend, got them in the vehicle to do the docked hot fire test, which I'll talk a little bit more about. They were anxious, excited, and happy to be there. You can tell every time they get in Starliner, they love the vehicle, they love Starliner, and they're so happy to be a part of the mission. I want to take a step back and talk about what we've been doing over the last two and a half weeks, or week and a half, I'm sorry. What we wanted to make sure that we reviewed all the data from the flight, including all the thruster firings from all the way at the very beginning of the flight, even on flight day one before the docking when we had the thruster fail-offs, and also do some additional testing and analysis on the ground that we could prepare for the undock, deorbit, and return. So we've been collecting as much data as possible. I'm going to take a little time today to update you on some of the observations we saw in flight, and I'll do that in a very detailed manner. Before we get into that, I would like to talk about the return date. We are now targeting an undock and return no earlier than June 26th. We've moved off of the 22nd. We want to give our teams a little bit more time to look at the data, do some analysis, and make sure we're really ready to come home. For this opportunity, it's a landing at White Sands Space Harbor on Wednesday the 26th at approximately 4:51 a.m. Eastern or 2:51 a.m. Mountain. An undock would be that Tuesday the 25th at about 10:10 Eastern for that landing. So we've moved that and gave them the time. We did that move also to allow our teams to have time over the weekend to take some time off. We felt like the team was working really hard, and it would be good to give our teams a bit of a break. We do have backup opportunities. As you can see, the pattern is about every 4 days we have a prime opportunity. So that prime opportunity on the 26th is to the White Sands, and the next one would be July 2nd, and that prime would be to Wilcox. So about every 4 days we hear that. ISS is happy to have Butch and Sunny to be on board the space station. We're putting them to work and getting a lot of good work out of them. They helped us with the docked hot fire testing. I do appreciate the space station program. Been really good at helping this mission with the docked hot fire test that I'll talk more about on Saturday, and then also some inspections of some of the thrusters that failed off using the robotic system on the space station. So what's really complicated is, we're going through all the data from this flight, but comparing it to OFT2, and also looking forward to the remainder of the flight and running simulations of the number of thruster pulses and the helium requirements for the remainder of the flight. So let's start with the thrusters. Last time that we spoke just after docking, I told you about 5 reaction control system thrusters. These were all aft thrusters that failed during the final phase of the rendezvous after we had done the TPI burn. In that final phase where there's a lot of thruster firings, we had 5 thrusters fail. Thruster B1A3, when we looked at that hot fire data, we saw that it had 11% thrust on one of the firings and then 0% on another. These were the 2 firings that we did on the rendezvous day. And so that thruster, we have decided we are not going to hot fire that thruster anymore. We didn't hot fire it on On Saturday, we're just going to leave that thruster alone because it shows a very strange signature where we're getting almost no thrust out of that. So we're going to leave that thruster deselected, and we're not going to use it for the remainder of the flight. We went through, during the hot fire, the first thing we did was a really short pulse, like a quarter of a second pulse on all the thrusters. And we hot fired all 7 of the thrusters, not B1A3, but all 7 of the thrusters, including, 3 of the good thrusters that we didn't see any. We saw very nominal behavior on rendezvous day. When we did that, we saw, really good what we call chamber pressure. And so chamber pressure is a way to measure the health of the thruster in terms of telemetry. I think of it as like measuring the health of your tires on your car. You check the pressure on your tires to see if they're healthy. It needs to be in a certain range. And these thrusters, when they fire, they normally have a chamber pressure trait that looks very normal. And so when we hot fired all the thrusters, they were around the 300 PSI, pounds per square inch measurement. Some were a little bit lower than that. It's really hard with the telemetry system we have to capture what we would call the peak of that thrust because we only have telemetry at 10 samples per second. So on S2A2, we had a good, that was the starboard, one of the starboard thrusters, had good PC. Also S1A1, the top T2A2 and B2A2 all had good chamber pressure. So each of those had a quarter of a second pulse, and we checked the thrust on that. So coming out of that, we feel very confident in the thrusters, and the team is just making sure to go look at the thrusters in detail across the whole flight and compare them to what happened on OFT2. If you remember on OFT2, during the rendezvous sequence, we had 2 thrusters fail. Both those thrusters came back at the end of the flight, and the team's looking at all that data and comparing it to OFT2. We also took advantage, and this is something that really helps us for future flights while we were docked to ISS, of using the ISS guidance navigation control system to look at the thruster firings. And the way we do that is we fire the thrusters each for about 1.2 seconds, and then we look at the response in the ISS flight control system to measure the acceleration from the thruster. And then also we can use it changes the rate on the vehicle a little bit. ISS weighs 1 million pounds, so it's a very big vehicle. But we can actually back out and see how it's trying to move the station by firing this thruster. So we did that for all 7 thrusters, and all those thrusters look like they have good thrust. In other words, that's the force that's coming out of each of those thrusters. So, for example, I just checked before I came over and looked at the plots. S2A2, S1A1, and B2A2 had almost 100% thrust coming out of that thruster, which means it recovered from the rendezvous day. And we have some theories about what's going on inside the thruster, where when the thruster gets very hot, and we had a lot of pulses and demands put on those thrusters during rendezvous, you can actually get not as good a mixing in the chamber. You need the oxidizer and the fuel to spray, almost like a shower head that sprays together the fuel and the oxidizer mix, and that produces thrust. And so in some cases, we think the heating may have caused the propellants to vaporize a little bit, and we didn't get good mixing, and that's why the thrust was a little bit lower. So remember, we don't get the hardware back. That's why we're taking our time to do this hot fire and collect all the data, and also taking our time to go through and review all the thruster firings for the whole flight, and again compare some of that data to OFT2. It does look like when we look at the 2 flights, the rendezvous was a little bit more demanding on the propulsion system. In other words, it fired thrusters a little bit more frequently, and it fired them in a little bit more rapid succession, and that caused a little extra heating. And so we're trying to understand that as well. We're also in the process of running a lot of simulations to look at the remainder of the flight. So we know what happened on rendezvous day with the thrusters failing off, and we're comparing what happened there to the remainder of the flight. And Michael talked a little bit more about the undock sequence and the SEP sequence. And, we have 2 big events, the deorbit burn. We want to understand how the thrusters will perform during the deorbit burn, when they are demanded to fire to hold attitude or hold the orientation of the vehicle during the deorbit burn. And then after that, they're really not used for the separation of the crew module and service module at the very end. Those are a different set of thrusters used for those. So the path forward is really over the next week. We really need to be working this week to try to wrap things up by this Saturday, the 22nd. Our teams are going to look through, and I listened to about a 6-hour review yesterday of all the thruster firing data. They're going to look at that thruster fire data again today and compare it to the GNC simulations. So they're spending time doing that over the rest of the week. On Saturday as well, we had an opportunity to look at the helium leaks on the helium manifolds and get another check of those leaks that I told you about in our post-docking press event. We did have one more leak registered that I was not able to tell you about on the 6th. It's a very small leak that we saw after docking. So that's the 5th leak. It's the smallest of all that we've seen, and very similar to what we saw on OFT2. So on the hot fire on Saturday, we isolated the helium manifolds again, and then we looked at those leak rates. And I would say every single manifold that we looked at, after 9 days being docked, we saw the leak rates going down. And we can provide the leak rates to you. For example, the port helium manifold 2, that's the one that we call the P2D2 flange leak. I'm going to use a little different units this time. It was 11.5 standard cubic centimeters per minute. That's standard cubic centimeters per minute after the docking when we closed the ISO valves. And then after the hot fire, it was 5.6, so it kind of had reduced in half again. Every single manifold, the leak rate had gone down. And so in terms of the helium leaks, we think somehow it's related to, although specifically we don't know the exact cause, it seems to be related to the activity of the thrusters. And if you remember, we saw 2 leaks on flight day 1 after we had done 2 OMAC burns, and then we had some crew flying activities that day where they were maneuvering to attitudes. We saw 2 leaks that day in top manifold 1 and port manifold 1, and then we saw 2 leaks after docking where we fired thrusters significantly on docking day. So it seems to be related to dynamic activity, and what we're doing on the helium leaks is now looking at what's left in the remainder of the flight and how many dynamic activities there are. We've looked at the margin for return. You know, I talked about we need about 7 hours of helium, and we have about 70 hours of margin to get to the deorbit burn. We're actually also doing some seal testing on the ground at the Marshall Space Flight Center. We're purposely damaging a seal, cutting the seal, and putting it in a simulated flange and looking at leak rates. We're also able to take that simulated flange, and heat that flange up and look at leak rates for that. And so we're spending some time doing that. So the path for going forward is to continue to look at the helium system, continue to try to understand what's happening. Again, look at simulations for the remainder of the flight. What's our demand? What if we wave off? And what does that mean for the system? And then the operational techniques to manage the helium system. Let's see, we had one more item we worked after between the docking and the post-docking and now. We had in the service module, this is a valve that actually is used to isolate propellants. So on the port manifold, there was an RCS oxidizer isolation valve. So this is a prop valve on the oxidizer side that was not properly closing. So the valve was moving clearly, but what we saw on the valve was it was not seating clearly. So in other words, we saw the valve move, but then there's a seat that actually needs to form a good seal so we don't see propellant moving after that valve. We used the other valve in that manifold. The A valve was the one that wasn't functioning. The B valve is now working fine. We used that to isolate the manifold as planned, and so we can work around that for the rest of the flight. This was different than what we saw, you may remember, on Service Module 2, on OFT2 in 2021. We had several oxidizer isolation valves that did not function during the pre-flight checks. This is different than that. We wanted to go ahead and cycle all the valves and make sure we didn't see any of the signatures that were similar to that service module. We know we had a good ground purge of nitrox and air the entire time from the C3PF into the VIF out to the pad. And so we confirmed that all the valves are functioning on the vehicle, and this signature looks a little bit different. So that issue is closed for flight, and we know how to manage it. We're going to talk a little bit more about some of the Mark Nappy will talk a little bit more about what we've been doing while we've been on orbit, some of the power-ups of the vehicle, habitability checks in safe haven. Meanwhile, we're getting ready for return in parallel to doing all the work on the service module that we need to do to convince ourselves that we have a safe vehicle for return. We want to also understand what this means for the long term. Can we get some data while we're docked that helps us with post-flight troubleshooting? Because sometimes what's interesting about the service module is the best place to do some of this testing is actually on orbit. where we can replicate the thermal exactly in the vehicle and have the entire dock houses connected to the rest of the service module, so the best place for the testing is on orbit. On the ground this weekend, and Mike will talk more about this, we did have a mission dress rehearsal. We had all the recovery teams in place at the White Sands Space Harbor. They went out and simulated a landing. They had the helos present, all the aspects of the NASA and Boeing teams, did a nice dress rehearsal of the end-to-end recovery process from the landing to getting the crew back to Houston, and even some contingency. So feel really comfortable about return now with that happening. Once we get through all the engineering data reviews, we'll focus on return. We really like the opportunity on the 26th because it's a great opportunity into the White Sands Space Harbor, and it's before sunrise, and so the wind should be very benign and the weather should be benign. Although it is difficult to predict the weather in the desert, and with the mountain ranges and terrain effects, we'll watch that very carefully. The crew's doing well. They've been very positive about the whole thing. They love Starliner. They love being in the vehicle. They love being on ISS. I think, if you ask Butch and Sonny, they might want to stay for a long period of time. I want to say how proud I am of the NASA teams. They've done a tremendous amount of work since docking. We have a little bit more work to go in front of us, but the teams are doing well. And we'll undock and land when we're ready. I'll turn it over to Dana.